Good afternoon, and welcome to the second panel in our symposium, Seeing Anew, the Detroit Observatory Yesterday, Today, and Tomorrow. Our panel will be discussing the Detroit Observatory in the history of astronomy. The observatory is certainly significant in the history of the university. It helped launch a transformation of the curriculum and, for that matter, of the faculty. It put U of M on the map. It brought students to U of M for what it symbolized and how serious U of M was as an institution, as a place to learn. And it even, through the activities of its first director, Franz Brunov, helped build the art collection of the university. But of course, if it had not had an impact beyond the U of M campus, it would likely have been long forgotten, and we may not even have it anymore. So this is what we're going to be talking about, and it's my pleasure to introduce our panelists in the order in which they will speak. Our first speaker is Patrick Seitzer, Research Professor Emeritus of Astronomy at U of M. Pat received his BS from Georgetown University and his PhD from the University of Virginia. His research centers on optical observations of space debris using ground-based and space-based telescopes, and he served on the NASA delegation to the Interagency Space Debris Coordination Committee from 2001 to 2015. Pat is also an historian of astronomy and of U of M astronomy in particular. He has been instrumental in saving and restoring the Detroit Observatory, and he served from 2017 to 2019 as chair of the Historic Astronomy Division of the American Astronomical Society. So welcome, Pat. Next will be Andrew Rutledge. Andrew received a bachelor's degree from the University of California, Riverside and a master's from the University of Chicago. He entered the PhD program in history here at Michigan in 2011. While a graduate student, he received several research and teaching awards, including a Fulbright Fellowship, and he earned his PhD in American history in 2018. After interning as a researcher for Native American photography at the William L. Clements Library, he joined the staff at the Bentley Historical Library in 2019, where he is research associate. Andrew has done extensive research into the history of the Detroit Observatory, greatly expanding our understanding of topics ranging from the original funding of the observatory to its involvement in timekeeping, which he will discuss today. Finally, we will hear from Sally Uy. Sally received her AD from Bryn Mawr and PhD from the University of Arizona. She studies massive stars and their effects on their host galaxies. One of her research programs investigates runaway stars ejected from star clusters, many of which are in tight binary systems. Her team has determined that almost all massive stars outside of star clusters are runaways that were rejected from their birth clusters through unstable orbital motions and supernova explosions in binary systems. Sally was a recipient of an NSF Faculty Early Career Development Award and the Annie Jump Cannon Award for the American Astronomical Society and American Association of University Women. She also is very knowledgeable about the history of the Detroit Observatory. In addition, she is the leader of Michigan Dark Skies, and she spearheaded the recent initiative that successfully brought about a new lighting ordinance for the city of Ann Arbor. So welcome to all of you, and Pat, take it away.
Okay, thank you, Gary, for that wonderful introduction. And what a pleasure it is to be able to talk today at the rededication of the Detroit Observatory. And our special thanks to the donors, the Frankels, for their major contribution to making this possible. So what I'd like to talk to you about today is the founding of the Detroit Observatory and how it became the birthplace of Michigan astronomy, and how astronomy and its facilities at Michigan grew from very humble beginnings. So it all started when Henry Philipp Tappan hired a German astronomer, Franz Brunov, to come and be the first director of the Detroit Observatory. And he introduced German methods, generalized and mathematical rigorous methods of astronomy and teaching them. And the observatory became the first research laboratory at the University of Michigan. And Bruno's contributions to astronomy may have been only for 2 years here, but his legacy has lived on significantly. So the instruments that were acquired originally were the instruments of classical astronomy, measuring when and where objects are. So there's a large telescope, which is the slide at the picture at the lower left, which is the 12-inch Fitz refractor installed in 1858, and which, if it's clear tonight, you'll have a chance to look through. And it was useful for finding asteroids and measuring double stars and the other things of classical astronomy. On the right side of my slide is the Meridian Circle, which also still exists today, and a clock. And so with the Meridian Circle, you can tell time if you know where you are, or you can measure the positions of stars if you know what the time is, but you can't determine both of them simultaneously. The large refractor was obtained from the United States. It was one of the first large refractors built in the US by the manufacturer Henry Fitz. The Meridian Circle and the clock came from Berlin. The Meridian Circle from the firm of Pfister and Martens, and the clock from the firm of TD is the only TD clock in the United States to the best of our knowledge. Now, I normally hate to show slides with lots of text on it, but this text from the book, The Launching of Modern American Science by Robert Bruce, is significant. In 1854, the German astronomer Franz Brunov came to the University of Michigan and offered the only course in the United States that taught the German method. It lasted only 2 years. It produced an able and outstanding teacher in James C. Watson, who carried on and strengthened Michigan prestige in the field. And Sally will follow up on that. This is the sentence that's most critical. By 1915, Michigan graduates made up a quarter of the leading American astronomers. By 1915, Michigan graduates made up a quarter of the leading American astronomers. Bruno had only been here for 2 years. He had taught Watson, and the educational foundation that was set had a significant result in leading American astronomy. Bruno's significance in transplanting and standards in astronomy may be likened to that of Agassiz in natural history, who was at Harvard. So had a very significant impact on modern American astronomers, even by 1915. But by 1908, the Detroit Observatory was looking a bit dated. Classical astronomy was being supplanted by astrophysics that tried to answer the question of why. Why do you see things happen? Not that they move. That's what classical astronomy did. And so by 1908, when Hussey returned to Michigan, he built a 37.5-inch refractor and a large reflector and a large extension to the observatory. And that the refractor or the reflector and its spectrographs were in that big dome there. I will return momentarily to the strange structure being erected on the outside of the observatory. One of the most significant discoveries in Michigan astronomy, which is still cited today, is the Rossiter-Mclaughlin effect. This was a 1920s discovery by 2 astronomers at Michigan, and it is still cited today in exoplanet research. So for people that are studying the planets around other stars, this effect can be significant. Normally, when a planet goes in front of the star, as the upper left slide shows, the light decreases and the velocity changes. The velocity change is the Rossiter-Mclaughlin effect. And 100 years later, so on the bottom right, you see on the left-hand side plot shows you how the light curve drops, how the amount of light coming from the star drops as the planet goes in front of it. But on the right, it shows you how the velocity of the star that it's measured changes. The star is rotating, and its velocity changes as the planet moves in front of it. It is still cited today, over 100 years later, and all I can say on this is go blue. So that was the first of the new facilities that the University of Michigan founded. The Lamont Hussey Observatory in South Africa was the first facility outside Ann Arbor, and it operated from 1928 to 1971, when it was closed due to conditions in South Africa. It was the largest refractor in Southern Hemisphere. It was used for double star research, measuring how 2 stars go around each other. Again, it was classical astronomy. But the observatory dome is still there, even though the telescope was scrapped. And in 2013, the University of the Free State converted it to a digital planetarium. So they hung a smaller dome inside the main dome, and the telescope was re-erected as an outside sculpture where visitors of many species can admire it. So if you happen to have a chance to visit South Africa, I encourage a visit to Bloemfontein. The next facility that came online was the Mcmath Holbert Solar Observatory near Pontiac, Michigan. It It was named after Mcmath, who were engineers, and Holbert, who was a judge. It started out privately funded. It started out making movies for educational purposes that were now available in the early 1930s. They were done with a small refractor and a motion picture camera attached to the back. They were some of the first movies made of astronomical effects. And that telescope, or that facility, was closed in the late 1970s, early 1980s, as better facilities became available in the American Southwest and on Hawaii. Finally, let's move on. There's not only optical, but there was the Peach Mountain Radio Telescope, which was built in the 1950s. And it was dedicated to long-term studies of radio sources from the 1950s until the early 2000s, when the funding finally ran out. It's still there. It's now operated by the Aerospace Engineering Department on North Campus for satellite tracking. The conditions in Michigan had deteriorated, and so Michigan astronomers were forced to look elsewhere for their telescopes and to have clearer skies. The first one was the Michigan Dartmouth MIT Observatory, located on Kitt Peak in Arizona, with a 2.4 meter Hiltner telescope and a 1.3 meter McGraw-Hill telescope. 2.4 meter, the Hiltner was named after Al Hiltner, the discoverer of astronomical polarization. The 1.3 meter was named after the company that funded its move from Michigan, where it replaced the 37.5-inch reflector, to Kitt Peak. Let me move on. The other telescope that's far away, that originally was in Michigan in 1950s and was moved to Chile in 1966 after what I like to say is 3 clear nights. But it was moved to the much clearer skies of the Cerro Tololo Inter-American Observatory in Chile. This is a wide field imaging telescope. The yellow arrow shows you where it is on the summit of Cerro Tololo, next to a 1 meter from Yale and the 4 meter Blanco telescope. It's used for wide field imaging. It did spectral surveys of stars, the Magellanic Clouds, and for many years it surveyed for space debris for NASA. So a quite broad range of interests. However, 0.6 meter and 2.4 meter telescopes are a bit small in this era of 10 meter telescopes and larger. So beginning in the early 2000s, the University of Michigan invested in twin 6.5 meter telescopes in Chile. The Magellan Project, BADA, and two 6.5 meter telescopes at Cerro Las Campanas in Chile, with partners the Carnegie Institution, Arizona, MIT, Harvard. And the reason is that, again, this was a case where the University of Michigan could not afford by itself to build such large telescopes, but in partnerships with others, it can do remarkable things. And so these are our prime research telescopes right now. But even looking forward to the future, more into the future, from the original 1854 observatory, the University of Michigan is the only United States university participating in the European Southern Observatory's Extremely Large Telescope, ELT, the 39-meter diameter primary mirror, which is being built in northern Chile. Again, it's the only U.S. university investing in this telescope, and it will be a prime research tool for University of Michigan astronomers in the future. And all of this flowed from Franz Brunov coming to the University of Michigan in the 1850s, starting an astronomy department, his brilliant student James Watson, and everything that flowed from that today. So that's all I have. Again, my thanks to the donors for making this event possible. And I turn it over to Sally, or I turn it over to Edmund. Sorry.
Well, before I begin, I just want to briefly thank Gary Kranz and Terry McDonald for inviting me to participate and to tell a story that is both fundamental to the world we live in today and also something we don't really think about anymore, is time. Because for thousands of years, the vast majority of people really had little need for or interest in knowing what time it was. Generally, a glance at the sky to give a sense of how long it was until dark or dawn was enough for most people. But it was only in the 19th century, when industrialization began, that started to change. As more and more Americans were drawn to the industrializing cities, their days were increasingly governed not by the movement of the sun, but by the chime of the clock. And along with the railroads that bound those cities together, this created a new need for widespread and accurate timekeeping. And solving that issue would put both the Detroit Observatory and the University of Michigan on the map of great American universities. Really, the story begins with the whistle of a railroad, because railroads were not only a key symbol of industrialization, they tied the U.S. together. Beginning with the first locomotive journey through Baltimore in the 1820s, railroads simply exploded across the United States. By 1850, the country had built more than 5,000 miles of railroad track. By 1861, over 30,000 miles had been built, stretching all across this country. At the time of the Civil War in 1861, more than 80% of Americans living in what is now the Midwest lived within 5 miles of a railroad line. And this railroad spread and the rapid travel speed really tied American society together in ways that had been unimaginable before this. Prior to it, when it took up to a week to travel between, say, Detroit and Kalamazoo, the 10 minutes time difference in local time determined by a sundial really made no difference to anyone. But when that same trip took only a couple hours, that 10 minutes time difference was a huge issue. And this difference became even more important with railroads because they had to need to find a way to track their train's location. And the solution that some very clever engineer came up with was to take the local time at one station, generally their headquarters, and set the clocks at every single station and every single train to that same time, no matter where the train was physically. This simplified the creation of timetables because you could simply print one based on your headquarters and use it everywhere. But however, this railroad time could be very different from a local time. So, for example, the Michigan Central Railroad, which was based in Detroit, used Detroit time for its railroad time. But that station in Chicago that they used had a local time that was 18 minutes faster than that. The issue was even worse if a town had multiple railroads. In Saginaw, Michigan, 4 different railroad companies traveled through the town, and they ran on 3 different time schedules: Chicago time, Detroit time, and Hamilton, New York time. All of these differed dramatically from local time, and many an unwary traveler caught themselves missing a train if they didn't pay attention. And this situation really wasn't much better within America's cities, where not only the railroads, but every clock tower ran on its own schedule. As the Detroit Free Press complained in one editorial, when a person speaks of Detroit time, they speak of a very curious and indefinite thing. The bells in the various towers strike at various intervals, often varying from 10 to 30 minutes of each other. And amidst all this jargon, the anxious inquirer after the true time is liable to become hopelessly confused. But as frustrating as those competing time systems were for Americans as they walked the streets of their cities or attempted to change trains in Chicago or Saginaw, they were also dangerous for those traveling the rails. In the first 8 months of 1853 alone, 66 railroad accidents left 190 people dead and another 400 injured. The most infamous of these was probably the one that occurred in Massachusetts in August 1853. On that day, a southbound train on a single line track was running behind schedule. Checking his watch, the conductor ordered the engineer to increase speed, thinking they had time to reach a siding before the northbound train reached them. He was wrong. 14 people died when the 2 trains collided, and dozens more were injured. Critics, of which there were many, accused the railroad company of supplying the conductor with a poorly functioning watch, and even worse, of failing to ensure that the clocks in the 2 trains actually matched. The disaster only added fuel to public outrage over both railroad accidents and public concern over the issue of time. One of those frustrated by all these inaccuracies in timekeeping on both a personal and a professional level was Henry Nelson Walker of Detroit, pictured on the left here. A lawyer, Walker had served as Michigan's Attorney General before becoming involved with Michigan's expanding banking and railroad industries. He was also the president of the Detroit Young Men's Society, probably the most powerful cultural group in the whole state, which hosted monthly public lectures and debates on a whole variety of scientific, historical, political topics. So for many reasons, Walker was really interested in the problem of time. And the solution to Walker's issue presented itself in the form of the University of Michigan's first president, Henry Philip Tappan. Tappan had long been a critic of the state of America's colleges, complaining in an 1851 book that, quote, "In our country, we have no universities. They have neither libraries and material of learning, nor the large and free organizations which go to make up true universities." When he arrived in Ann Arbor in 1852 to become the University of Michigan's president, Tappan gave a speech outlining his vision for a new type of university. Drawing on the German model of education, he sought to transform Michigan into an institution where knowledge was not just taught, but also created. Because he argued that learning must be valuable to all of society, not just to students. For, quote, "Literature, science, the arts, educational apparatus, and labor all increase the commodities of trade and all add to the national wealth." And in service of that vision, he proposed creating America's first scientific curriculum, incorporating mathematics, civil engineering, chemistry, industrial arts, and of course, astronomy with the use of an observatory. Now, one of those listening in the crowd that day was Henry Walker. He identified with Tappan's vision, approached the president afterwards and asking how he could help him. Without pause, Tappan immediately responded he could help by funding the construction of an observatory. Walker then arranged a meeting for Tappan with other prominent Detroiters who agreed to donate funds for the project. In gratitude, Tappan named the planned building the Detroit Observatory, even though it was in Ann Arbor. Tappan would later comment that he'd only contemplated to secure a large refracting telescope and erect a suitable building for it. And that telescope would be the Fitz refractor that's under the dome today, and you could see at the viewing tonight. But Walker suggested adding a second telescope to the project, the Meridian Circle. And although neither man was really aware of it at the time, the observatory and that telescope would solve the problem of time for Michiganders. Now, a Meridian Circle is a very specialized type of telescope, and it was really at the cutting edge of astronomical technology since its development in the 1700s. This type of telescope is designed to point only along a north-south line, known as a meridian, and unlike other telescopes, cannot swivel left or right at all. And when an object, such as an asteroid, appears in front of it, the telescope is used to make two key measurements: the time at which it crosses the meridian as it travels from east to west across the sky, and its angle above the horizon. From these, the object's location, the night sky can be recorded and tracked. Now, this is a celestial coordinate system used by astronomers. It's similar to longitude and latitude we use down here on Earth, but astronomers, for various historical reasons, use the terms right ascension and declination for these two coordinates. Now, like latitude, declination measures an object location above or below the horizon. Right ascension and longitude similarly both measure an object's location east or west around the planet, but unlike longitude, which uses degrees to measure an object's location east or west from the prime meridian in England, right ascension is measured in hours, minutes, and seconds of sidereal time. Now, sidereal time is a very specific system of time used by astronomers, and it's very different from solar time that's used in everyday timekeeping. Now, a solar time is based around the idea of a solar day. That is the interval between two passages of the sun overhead, from sort of noon to noon. In contrast, sidereal time is based around the sidereal day, which is the amount of time it takes for a star to pass directly overhead. Now, the difference between these two types of time can be seen in these two images here. Now, imagine you're standing in Ann Arbor looking up at noon, and that there's a sun and a star both directly overhead. Now, due to the Earth's orbit around the sun, it actually takes more than a full 360-degree rotation of our planet for that same spot on Earth to be facing the sun again. Because if you think about it, not only is the Earth moving around the sun, to get that rotated, it has to go like this so you can see directly ahead again. In contrast, stars are so far away that the Earth's orbit around the sun makes absolutely no difference to how long until that star is directly overhead again. And so a sidereal day is actually slightly shorter than a solar day, but it's more consistent because it doesn't change based on the Earth's orbit. And it's for that consistency, which is why it's used by astronomers. To track these celestial coordinates and use sidereal time, Henry Walker personally donated $4,000, equivalent to about $130 in 2020 money, for the Detroit Observatory's Meridian Circle. And President Tappan then traveled to Europe, where he commissioned the creation of one of the finest telescopes in the world. With a magnifying power of up to 288 times the human eye, it could see nearly anything in the night sky, while a spider thread set into the lens allowed for the precise marking of the passage of stars in front of it. To calculate declination, the two rings on either side of the telescope, these sort of wagon wheel-like things you can see here, are covered with angle markings so small and precise that they could only be read with a microscope. To accurately measure right ascension, astronomers require absolute precision in timekeeping. And so placed on the pillar next to the Meridian Circle is an instrument that the Detroit Observatory's first director, Franz Brunov, insisted be created alongside it, a sidereal clock crafted by C.F. Teyde of Berlin. The clock's accuracy and location made it easy for an astronomer to record the precise timing of the passage of an object in front of the telescope. Then, together with the declination taking from the Meridian Circle's rings, the astronomer could calculate its celestial coordinates as seen from the observatory here in Ann Arbor. This system was set up and created by the observatory's first director, Franz Brunov. Hailing from Germany, Brunov was undoubtedly the best trained and certainly the most thorough astronomer on the continent when he arrived in Ann Arbor in the 1850s. So demanding were his standards that he spent almost 4 years calculating and adjusting for every possible source of error, both internal and external, that could have any influence on the Meridian Circle's accuracy. The key element to this process of deciding errors was setting the sidereal clock. To do this, Brunov took the celestial coordinates of an object already seen at other observatories and compared those coordinates with his own observations here in Ann Arbor. By comparing their different right ascensions alongside the Detroit Observatory's longitude, he was able to calculate the correct sidereal time for the observatory. And once he had set the observatory's clocks to that true time, the local solar time, which people like me and most other people use for our everyday timekeeping, could be calculated with extreme accuracy. Now, Brunov declared the Detroit Observatory completed in 1857, but it was only 6 years later that it really began to provide relief to time-addled Michiganders. On September 11th of 1863, the observatory's second director, the brilliant James Craig Watson, grandly announced to Detroit's newspapers he had reached an agreement with the jeweler Martin Smith to send, quote, by telegraph at 5 o'clock p.m. precisely the correct time for York City, derived from transits of stars observed at this observatory. From that day on, every morning, an employee of Smith's would haul a 4-foot diameter red canvas ball up a pole on the business's roof. You could see the ball and the pole in this picture from the 1880s. The latch holding the bowl at the top of the pole was connected by telegraph to the observatory here in Ann Arbor. When the clocks at the observatory showed 5 o'clock in Detroit, Watson would strike a telegraph key, causing the ball to fall. The sight of that large red ball dropping from over 150 feet above the ground was visible to most in the city. And soon, public clocks and churches began using this new city time supplied from the observatory. And so, for the first time, time in Detroit became standardized. Now, this use of time balls was something that was popular in a lot of cities in the US and in Europe in the late 19th century, and some of those time balls still survive. The most famous one, of course, being the one in Times Square in New York City, which still popularly marks the start of the new year every year, with a lot more fireworks than Watson's. In the wake of this new time service, the Michigan Central Railroad decided to adopt the observatory's Detroit time across its entire operation, which stretched outward from Detroit west to Chicago, south to Toledo, Ohio, north to Mackinac City, and east across Canada to Buffalo, New York. Altogether, time was sent along more than 1,000 miles of track from Ann Arbor. And as this new, more precise and regular railroad time spread, many towns along its tracks decided to end confusion caused by using their local times. Instead, they decided to adopt the time displayed on the clocks of their local railroad station. And so a uniformity in time began to emerge across the Midwest organically. Then, in the early 1880s, a group of railroad engineers took the next step when they adopted a plan proposed by an alumnus of the Detroit Observatory named Cleveland Abbe to create just 5 standardized time zones, each an hour ahead or behind those bordering it. The borders of these time zones ran through major cities' railroad stations, probably unsurprising if you consider there was a group of railroad engineers who created them. And so, for example, the border between the new Eastern and Central time zone ran through Detroit, Buffalo, Pittsburgh, Atlanta, and Charleston. This just the line between the yellow and blue in this map here, which is just a little bit different from our time zones today. However, the standard time system, as it was called, remained an unofficial system. Detroit continued to insist on using local time, as did Ann Arbor, even though the University of Michigan itself decided to adopt standard time. So as a result, actually, for almost a decade, the town ran 25 minutes faster than the campus. Possibly the origin of Michigan time? Now, the Detroit Observatory, despite this confusion, continued sending time signals for almost 40 years, only ending in the early 1900s. And throughout that period, Americans continued to operate under a variety of times. It wasn't until 1918 that Congress passed a law as part of the war effort during World War I that created 4 official national time zones. Michigan was placed in the Central Time Zone. But in 1933, the time changed again when the Michigan State Legislature, pressured by businessmen in Detroit, petitioned Congress to switch to Eastern Time. This was granted, except for a few counties of the Upper Peninsula which remained on Central Time. And there's been a little shifting back and forth since then, but that system is where we still are to this day. Now, unfortunately, however, Henry Tappan failed to see his observatory's contributions to standardizing time. In June 1863, just 3 months before Watson began his time service, he was dismissed by the university's Board of Regents over a decade's worth of clashes and controversies over a variety of issues, including his so-called Eastern errors, his support for a foreign German system of education that nativists opposed, and the cost of building the observatory. However, he had nevertheless transformed the University of Michigan into a place where knowledge was created, not just taught, and where public service was a core element of its mission. Now, Sally's going to tell you a little more about Watson and his achievements.
All right, thank you so much, Andrew. So I'll be going over one of the most important science legacies of the Detroit Observatory, which is, of course, an important Michigan legacy. James Craig Watson was the Detroit Observatory's second director, and he was director from 1863 to 1879. He himself was born in Canada, somewhere near London, Ontario, in the rural areas north of Lake Erie. And his family had very humble means. So the family moved to Ann Arbor around 1850 in hopes of a better life. But Watson himself had to work a number of menial jobs as a young teenager, but nonetheless was extremely motivated as a scholar, self-educated, taught himself Greek and Latin to the extent that he was able to enroll at the University of Michigan in 1853 at the age of 15. Watson was absolutely a prodigy. It was said that he even could translate Greek and Latin better than the professors that were teaching Greek and Latin, which he was studying at U of M, together with astronomy, where he was clearly studying with Brunov at that time. As an undergraduate, Watson also built himself a 4-inch telescope. So Watson was technically very capable, a keen experimentalist, as one can see from this, having ground the lenses of the telescope himself and so forth. And at the same time, he was also brilliant mathematically and theoretically. He had translated a German textbook on optics by the time he graduated as well. He graduated at the age of 19 in 1857 with his bachelor's degree, which was also the year of his first publication in the Astronomical Journal, which was calculating the orbital elements of a comet that had been discovered earlier that year. A couple years later, he obtained his master's degree and was put on the staff at the Detroit Observatory. By the age of 20, he already had 15 publications. And in that year, 1859, it turned out that Franz Brunov decided to leave Ann Arbor, and he went to the Dudley Observatory in New York. For this, Watson had an opportunity then to become the professor of astronomy, as he was appointed by the regents. And he was also put in charge of the observatory, although not named the director at that time. Turns out that Brunov came back to Ann Arbor the following year, 1860, moving Watson now to the position of professor of physics instead. Around this time, he was giving popular talks about astronomy, and he also wrote his first book, a popular treatise on comets. And at the same time that year, he met and married a woman from Dexter, Michigan, Annette Waite, who was said to have been someone also very keenly interested in his work and who occasionally helped him with it. So why did Brunov move to New York and then come back again? This has to do with the prominent American astronomer Benjamin Gould. Gould was the founding director of the Dudley Observatory, and this was in Albany, New York. And Gould, the vision for the Dudley had been something modeled on Michigan, that basically there would be a great university that would be built around this observatory. Unfortunately, they didn't have enough money for that. And so there were questions about the role of the observatory, and there were therefore some conflicts of ideas. And Gould was fired by the trustees of Dudley, and they replaced him with Franz Brunov. So that's why Brunov went to Albany, New York. However, he didn't last there very long either. He returned to Ann Arbor the following year, as we saw. Gould, however, was a very important figure in early American astronomy. He was the founder of the Astronomical Journal, which was the premier journal of record, the academic journal, which still exists today in that role. He was also a founding member of the National Academy of Sciences, which was founded in 1863. This was right around the same time that Watson's career was getting started during the Civil War. And Gould also was a founder of the National Observatory of Argentina at Cordoba in 1870, and he spent a number of years there mapping the southern sky. Gould's specialty was, in fact, astrometry, which is measuring the positions of objects in the sky, as Andrew described in wonderful detail for you. Gould developed some techniques to improve the accuracy of this by taking into account systematic errors from multiple observers that allowed him to increase the accuracy by which one could measure positions of stars by a significant amount. And he may have been the one who invented the idea of having astrometric standard stars. Standard stars are stars whose positions are more accurate than all of the others and meant to be used as references, basically, for obtaining the relative positions of anything else you want to measure. So if these red dots are the best, most accurate positions that you know, then if you want to measure the position of anything else in this field, you can just measure its position relative to one of these standard stars. So Gould had published a well-known set of these standard stars for the North Circumpolar Zone. And he also was able to do that based on a data set from the US Naval Observatory that had become available during the Civil War. Somehow Watson got involved in this project, and Watson was to take on the ecliptic zones, a much larger area of the sky, and he was going to publish sky maps, very accurate sky maps, once again, and astrometric standard stars, presumably using Gould's methods. However, he did end up spending about a decade on this work and never publishing the promised sky maps, perhaps because he ended up getting sidetracked. So why is this so important? As Andrew mentioned, if you have very accurate positions on the sky of all of the stars and you've made a very accurate sky map, then you can check after a period of time to see if something has moved. And if something has moved, then you know that you've got an object in the solar system rather than a star. And Watson started finding these objects, which is probably why he started getting more interested in that than actually publishing the astrometric maps. In 1863, Franz Brunov left Ann Arbor for good, and Watson was named observatory director and professor of astronomy. And during that same year, he discovered his first asteroid, the 79th to be discovered, and he gave it the name Eurynomy. So this is the publication announcing that discovery. It says, a new minor planet, number 79, discovered by James Watson, director of the Observatory of Ann Arbor. And the planet was of the 10th magnitude. Watson became a prolific discoverer of asteroids. By the time he died, he had discovered something like 10% of all the asteroids known at the time. And in the year 1868 in particular, he discovered 6 of them. This was a record for 1 year and quite an accomplishment that won him the Lalande Prize of the French Academy of Sciences a couple of years later. That same year, he published a textbook called Theoretical Astronomy. This was quite different from the popular treatise that he had written before. Now we have a comprehensive textbook that allowed that described in great mathematical detail how to calculate the motions of gravitationally bound orbiting bodies. And this was so comprehensive and thorough that it became a standard textbook in the field for decades. It was in print until 1900, and in fact, which was long after Watson's death. And it was, in fact, even reissued in 1964 by a different publisher, almost 100 years after its original publication. Another interesting asteroid that Watson discovered was number 139. So by 1874, Watson had become a very prominent figure in American astronomy himself, had been charged by Congress to lead the US expedition to Beijing to observe the transit of Venus across the face of the sun. This was a very important assignment and was going to lead to some of the most accurate measurements of the distance between the Earth and the sun. So very fundamental measurement of great importance. While he was in Beijing, he just happened to discover another asteroid, number 139, and he invited perhaps the most influential person in China at that time, a man named Yi Xin, who was generally known as Prince Gong. Prince Gong had, until very recently, been the regent for the underage emperor of China. And he invited Prince Gong to name this asteroid. And so the name chosen was Star of China's Fortune, Juehua Xin, which was abbreviated to Juehua. On his way back from China, Watson stopped in Egypt, and there he helped the Egyptian military with a geodetic survey, an assignment that took quite some time and that he did completely pro bono. And of course, this meant he had been away from Ann Arbor for quite a long time. I believe it was more than a year that he was not in Ann Arbor. And so the students, when they graduated in 1875, have a yearbook drawing in which they show Watson in the uniform of the Egyptian military. And the caption says, "Our star is in the east," referring to Watson, 10th magnitude. So why are these asteroids so interesting? Many people think that they're just little rocks that are orbiting out there and quite boring. They are, in fact, little rocks. They're maybe hundreds of kilometers in size. But this was a period when we were only just discovering exactly what was out there, and that the kind of the number of these objects and their orbital properties and so forth. It was a very exciting time to learn that there was, in fact, another component of the solar system. And all of these objects, for the most part, most of them were between the orbits of Mars and Jupiter. But you can see from this graphic that many of them also cross the orbit of Earth, and therefore there is some risk of an existential threat to humans, for example. But it turns out that these asteroids are relics from the formation of our solar system, and therefore one of the principal means that we have that are relatively accessible to us for studying the primordial matter of our solar system. And in fact, this is an example here of a mission. More and more probes are being launched to asteroids. This mission launched in 2018 is going to bring back a sample of asteroid material back to Earth next year. So the first asteroid was discovered in 1801, and by analogy, interestingly, almost 200 years later, it was discovered that we have additional objects in a similar belt called the Kuiper Belt. In 1992, the first Kuiper Belt object was discovered, and we are now in a very similar analogous phase of discovery where we're just trying to figure out how many of these things there are, what they are, why they're there, and what their link is to the origins of our solar system. In 2019, we had our first flyby of one of these objects. So very parallel in the discovery of the asteroids to the Kuiper Belt. Watson, unfortunately, did not live very long. He died at the age of 42 in 1880. This was just after he had moved to Wisconsin to help launch the Washburn Observatory. But he did leave in his will perhaps the bulk of his estate to the National Academy of Sciences. And he had two purposes in mind. The first was to endow a fund to calculate the orbital solutions for the 22 asteroids that he had discovered. In part, perhaps to make sure that these asteroids would not be lost, because there was not a whole lot of observational data for them. And asteroid orbits are kind of complicated, especially due to the perturbations of Jupiter and Mars. So if you don't have a good orbital solution and you don't have a lot of observations, the asteroid will become lost. So the endowment was to actually try to calculate, the charge was to calculate good orbital solutions for his asteroids. The second purpose was to fund a scientific award, the James Craig Watson Medal, which also comes with a monetary award. And the first winner of this award, fittingly, was Benjamin Gould in 1887. Almost 30 years later, Armin Loischner won this award in 1916, and this award is still given out today. Armin Loischner was the person who actually led the orbital calculations that were charged in the first part of Watson's will. So Loischner was also a graduate of the University of Michigan. He obtained his bachelor's degree in 1888, and he had worked with a person named Martin Schaeberle. Martin Schaeberle had been Watson's student, and in the late 1880s, Schaeberle was doing most of the astronomical work at the observatory, but he himself was not the director. So he was lured to California to help launch the brand new Lick Observatory of the University of California. Interestingly, another Michigan graduate, William Campbell, who obtained his bachelor's degree in 1886, also working with Schaeberle, also ended up in California, as did Loischner. Both of these people went to California in the early 1890s, and I have to infer that they were invited there by Schaeberle. And both of these men, Loischner and Campbell, turned out to be extremely influential in the origins of the Berkeley Astronomy Department. Loischner was the first chair of the Berkeley Astronomy Department and held that position for over 20 years. And Campbell was one of the very early directors of Lick Observatory, which was linked to the Berkeley Astronomy Department at that time. Campbell held that position for about 20 years until he was named president of the University of California. And I'm also showing in this image of the Lick Observatory staff in 1911, H.D. Curtis, who was one of Michigan's most well-known faculty members as well. He was at Lick during the early 20th century, also for about 20 years, around the same time that Campbell was director there. And Curtis famously was a participant in the Curtis-Shapley debate that people may know of. But he came back to Michigan later and became one of our most distinguished faculty members. So in 1901, the Watson trustees of his fund charged Armin Loischner to be the one to calculate the orbital elements of Watson's asteroids. As I mentioned, this is a huge undertaking. There wasn't a lot of data. The orbital calculations are extremely complicated. And by then, one of the asteroids even had been lost already. So this was no small undertaking. And the funding ended up being able to support Loischner's career with many students and postdocs over decades. And in fact, Loischner did spend his whole life working on this project, among other things that he also did. But interestingly, a number of the people who held key roles in this work were women. So one of the earliest was Adelaide Hobey, who's down near the bottom of this image. She was Loischner's student around 1900 and was able to stay on in a research assistant role for a number of years on this project. And then a couple other women who held leading roles in this project were Estelle Glancy and Sofia Levy, both of whom did PhD theses doing these orbital calculations. It was, as you might understand, difficult for women to get jobs in astronomy at that time, especially at the PhD level. So unfortunately, neither of them were able to obtain faculty jobs in astronomy. However, Estelle Glancy did, after she graduated, go to Argentina, where she worked in the National Observatory that Gould had founded for a few years. She came back to the US, was not able to get a job, and therefore went into industry, where she was highly successful and I believe obtained something like a dozen patents for her work in optics, having to do with eyeglasses and contact lenses and so forth. Sofia Levy also did not get a position in astronomy. However, she did get an administrative position in the math department at Berkeley. and then eventually did get a faculty job and worked her way to full professor in math. Both Glancy and Levy did continue to collaborate with Loischner over a number of years, still working on the calculations for orbits of Watson's asteroids. And in the Q&A, if anybody is interested, I could also tell an interesting anecdote about Curtis and Adelaide Hobie. So why were these orbits so important? Once again, besides just trying to keep track of the asteroids themselves, the orbits are the fundamental parameters that we have for these objects, and they can tell you a lot about the previous history of the object. This plot shows you the orbital tilt versus the orbital radius, and you can see for the vast majority of objects that we know that are shown here that a lot of them end up clumping like this. And those clumpings clearly suggest that those objects which have orbital properties in common must therefore also have some origins in common as well. And so that allows us to then start picking apart what may have been going on with them, what they, how they originated, and information about the early solar system and so forth. So these are called families when they have orbital properties in common like that. And Watson, of course, also had an asteroid named after him, number 729, Watsonia. And that turns out to be the prototype of a family of asteroids, the Watsonia family. And it's been more recently discovered that the Watsonia family has a peculiar property that is characteristic of what are known as barbarians. Barbarians are also asteroids that are named after asteroid number 234, Barbara. And the barbarians seem to have an unusual polarization in the reflected light from the sun. That has something to do with the composition of these objects. They have a mineral called spinel, and that speculatively has been tied to them being linked to some of the very earliest of the solar system material, even for the asteroids. That is still a speculation, however. So basically, Watson's scientific legacy and that of the Detroit Observatory, Detroit Observatory continues to grow and evolve, and it's very interesting to see where it will lead next. Thank you very much.
Well, thank you, Sally, Pat, and Andrew, for those wonderful, wonderful talks. You know, there was a lot of information packed into these talks. It was great. I want to start with expanding a little bit on the statistic that Pat gave, that by 1915, a quarter of leading astronomers were from the Detroit Observatory. And Sally, you just laid out for us a half dozen people, I guess, who were part of that legacy. And I sort of want to ask two questions. One is, other prominent figures that we might want to know about, who might you mention? And the other thing is just your comments on sort of how this works. I mean, this sort of the sort of genealogy of science, I guess, as it were, or of scientists within a community. So, any comments along those lines?
Well, it is extremely interesting. There is an American Astronomical Society project called the Astro Genealogy Project, which attempts to do the family tree of astronomers and their students and their grandstudents and grand-grandstudents. So you can link all of them together with that resource. It's clear that in astronomy, sometimes just a few people can make a huge difference. And at Michigan, Brunov made that difference. And then Watson, as Sally pointed out, made that difference. So, you know, a key few people will make that difference. Now, some of the students that came out of Michigan didn't go on in astronomy, like Cleveland Abbey went on to become head of the Weather Bureau. But it was the training, the rigorous technical training that they received in astronomy at the University of Michigan, which enabled them to move on even into other fields. So I'm going to kick that question over to Sally and let her continue. Sorry, Sally.
Well, I think what's interesting about this and what I've learned from doing the preparation for this talk, which was fascinating, was that some of these influential people that Pat alluded to can be relatively obscure. Like Martin Schaeberle, for example. I had no idea about Martin Schaeberle. And he's not in the Astro Genealogy project. I actually went and submitted his name to them as a result of this. Because when you look at William Campbell, who was very, very well known, president of the University of California and so forth, you look him up in the Astro Genealogy project, and it doesn't give who his advisor is. And that was Martin Schaeberle, this obscure person who in turn was the student of Watson, who in turn was a student of Brunov. And I think a lot of people don't know about Brunov either. Brunov played such a key role here, but he himself, at least in the US, is a relatively obscure person also. Yet look what he created. If it weren't for Brunov and his rigor and his teaching of Watson, things could have turned out somewhat differently.
Right, yeah, and that's one of the things I think we want to do at the observatory is try to raise the profile of some of these people, Brunov and certainly Schaeberle, who did a lot of fascinating things, including discovering 2 comets while he was here, and while he was basically carrying forward the astronomy program at the observatory, while the director, Harrington, was much more interested in meteorology and other fields.
So can I mention a few more comments? There's any number of observatories that were founded at the same time as Michigan's, or perhaps slightly before or slightly after, that basically faded into obscurity until one person would come along and reinvigorate them. By the end of the 19th century, Michigan astronomy was fading into irrelevance with the construction of the 60-inch telescope and the 100-inch telescopes in California, the 40-inch refractor at Yerkes. And it was when Hussey returned and started the 37.5-inch reflector and the work on B stars that have emission lines. So sometimes just one person can start that process. So Watson did a great job. So did Bruno, and it's somewhat surprising Bruno is not more known today.
Mm-hmm, mm-hmm.
If I can add on to that about Brunov, it's being the right person at the right time. One of the people that Tappan originally asked they wanted to be director was Benjamin Gould. And instead, Gould took the position of the observatory in Albany. And there were a whole series of fights between Gould and the founders of the observatory. And Gould ended up barricading himself literally in the building for 6 months until Brunov was called in to diffuse the situation and take over. So, imagine if that had happened here in Ann Arbor with the Detroit Observatory, we probably still wouldn't have the building. So the right person at the right time really made the difference for the Detroit Observatory.
So speaking of battles, if I can use that as a segue, here's what a question from the audience is: can someone speak to the rivalry between James Watson and C.H.F. Peters in terms of asteroid hunting, which was a very public sort of rivalry? Sally or Andrew?
Andrew, can you take that? I know a little bit about it, but not much.
Sure. C.H.F. Peters was another one of really the leading astronomers in the U.S. in the mid-19th century. He was based in another one of the observatories that was really prominent at the time, but has faded into sort of obscurity. I think it was Hamilton, New York. Actually, where that time source I mentioned was. And he was even more prolific when it came to finding asteroids than Watson. Watson ended up with, what was the number, Sally?
22.
22. But C.H.F. Peters found 48. And
over a longer period.
Over a slightly longer period. Yeah. And their discoveries were really played out in the newspapers. Everybody announced, Watson found an asteroid this night, and Peters would respond a week later with, I found 2 asteroids. And there was this great sort of public rivalry as part of this broader popular interest in science in the 19th century. And even though they collaborated, Peters and Watson were very much concerned about being seen as the preeminent astronomer in the country. And that's one of the reasons when Watson tried to find Vulcan, which I think was mentioned in the first panel, Peters was one of his fiercest critics in the newspapers and among other astronomers. And I've actually found he made up insulting ditties that he had printed about Watson's efforts, saying, he doesn't know what he's doing. And so it was this really interesting, fierce public rivalry between two very sort of egotistical individuals.
Yeah, although what I read about it was that that it was much more of a personal vendetta on the part of, sorry, what was his name? Heinrich
Peters?
Peters, thank you. It was a much more personal vendetta on the part of Peters, and that Watson was kind of more, he was like, well, history will show me right. He was more kind of go with the flow on it, and he was much more focused on his work at hand. So yes, there was this huge rivalry, and Watson had a big ego and was concerned about his accomplishments and legacy. But I think it wasn't as directly combative and personal about things the way that Peters was, from what I read.
So there's a question in the chat about the role of spectroscopy, and I think we know, Pat, that it didn't really start at U of M until the larger telescope was in place. But Watson actually tried to get a spectrograph, right? I mean, he submitted a request, and Andrew, you might remind me of the year if you know, but he was turned down by the Board of Regents, right, for his request of spectroscopic equipment. Right?
I think that was the early 1870s, but I don't know the exact year.
So anyway, I Andrew's the only historian on this panel, right? Officially, only one with a PhD in history. So I'm going to ask. You can recuse yourself if you want, but I'm gonna ask you guys to engage in a little counterfactual history. Suppose Watson had succeeded in getting a spectrograph, basically 20 to 30 years before it came to U of M. What might have happened to the U of M astronomy during that period?
Well, he would have had a spectrograph on a 12-inch telescope, and he could have done it visually, which people were doing at that time. The photographic material was just starting to come online, but it really wasn't the photographic. It wasn't until the 1890s that photography really took off. And so you might have gained 10 or 20 years, but he would have been dealing with a visual spectrograph on a small telescope. And until you get a large telescope without chromatic aberration that you can do spectroscopy on, it's going to be pretty much, well, we say qualitative. Now, Secchi did a tremendous amount of work in classifying stars using visual spectrographs on various Jesuit observatories. But the quantitative measurement of radial velocities, of the strength of emission lines and things, of the astrophysics of it, really would have to wait until the advent of spectroscopic photography.
But just to totally speculate, I think, Watson was of the kind of brilliance that he could easily have become very fascinated by this and been lured to a different observatory that was bigger with a big, with a spectrograph, and could have started working in that field. Because he's smart enough that he could certainly easily switch if he thought that was interesting.
Yeah, and so there was, once photography came along, one of the Slipher brothers did the first measurements of the radial velocities of galaxies on I think a 24-inch refracting telescope. So it really waited for the discovery of photography, I think. Mm-hmm. Mm-hmm. And when that came along, if they had been investing in photography very early, then the Detroit Observatory could have gone in a completely different direction.
Mm-hmm. So we have a couple of questions related to the time service. One is, how did the finances of this work? I mean, was there a subscription service, as was the case at some other observatories? And then there's a question, can you comment on the U.S. Naval Observatory seizure of standard time for the nation and how that affected transit telescope timekeeping at the Detroit Observatory? So maybe Andrew, if you could, can you respond to the question about the subscription service?
Sure, but first I just want to apologize. My internet's acting up.
Yeah.
So to make it a little easier for everybody to hear me, I've stopped my video. Hope that helps.
We've lost Sally too, so I hope we can get her back. But go ahead with the
But yes, subscriptions were for time service were a main way a lot of observatories kept themselves going. For example, the Cincinnati Observatory, which was completely privately funded, unconnected to any university, relied entirely on money from railroads for its time service to keep it going. And in the Detroit Observatory, we don't have any records of a subscription service, but we do have something that's a little suspicious. Watson was a brilliant astronomer, but he also had a reputation for being somewhat venal, maybe because of his sort of impoverished childhood. But he was involved with a lot of businesses, a lot of sort of semi-questionable activities were charged to him. And it's noteworthy that while we have no record of a subscription being paid for time service, in 1874, the year Watson was in China, his assistant Shaberly, who was running the observatory in his absence, deposited $1,500 in the university's accounts with, we don't know from where, but it seems plausible that was a time service subscription.
Mm-hmm. So the thrust of the other question is the eventual role of the U.S. Naval Observatory in time setting, and what was the impact of that on sort of local observatories like U of M?
So the Naval Observatory was part of the Coastal Survey that was discussed briefly in the first panel today. And one of its main goals was to keep track of longitude for every location in the U.S. And it had the benefit that a lot of other observatories didn't, that it was technically part of the Navy, so it was under military jurisdiction. Its funding, so there was greater discipline for its astronomers and those working there. It was also funded by the government, so it could sort of undersell other institutions like the Detroit Observatory or Harvard's observatory when it came to offering a time service. So with the spread of the standard time zones beginning in the late 1880s, a lot of railroads decided to go with the Naval Observatory because it was cheaper than continuing to pay private observatories. And so over the course of a decade or so, the Naval Observatory began sending more and more time all across the country. And it basically undersold a lot of the private or university observatories in that period.
Sally, I think we're all dying to know the anecdote about Curtis and I'm blanking on the name now.
H.D. Curtis and Adelaide Hobie, right?
Yeah, Adelaide Hobie, yes.
Yeah,
right.
that had nothing to do with Watson, so I didn't want to take the time. But so I stumbled across this fascinating story too, which some people may already know. H.D. Curtis is famous for the Shapley-Curtis debate, in which he took the right side that spiral nebulae were island universes, i.e. they were galaxies that were, at cosmological distances. And so that's one of his great claims to fame. But apparently he was on the wrong side of another big controversy that could have, been extraordinarily embarrassing for him, which was Einstein's theory of general relativity. So there were these observations by Eddington, and I don't know whether this refers to other people's observations, but when the sun was in total solar eclipse, you can see the stars that are right in the same field because the sky is dark. And a big test of Einstein's general theory of relativity was to see if you could see gravitational lensing, the distortion of the positions of these stars very close to the image of the sun because of the sun's gravity. And Curtis did calculations that he thought demonstrated that Einstein was wrong and that those observations were not, in fact, there, confirming that. And he was going to publish this. In fact, it had already been announced sort of, I think, at some meeting, but he hadn't actually published it. And he was in the process of moving someplace else, I think to Allegheny Observatory, maybe. This was in his last days at Lick Observatory. And I think Campbell asked Adelaide Hobie to just double check his calculations because she was the smart one, right? And it turned out that, in fact, she found numerous errors in his calculations and couldn't even make sense of some of them. And, Campbell asked him, well, Adelaide has found like some errors here and some errors there. And Curtis said, oh, yeah, I guess it's quite possible because, I did that in haste, or I don't know what. He conceded that he could have made mistake. And so they did not end up publishing that result. And so Adelaide Hobie saved him from a terrible embarrassment. And instead, Curtis became famous for his position in the Curtis-Shapley debate.
That's great. That's great. So we're just about out of time. I mean, I wish we had more time for some discussion, but we have another panel coming up in about 17, 18 minutes. I wonder if I could just end this with asking each of you to think a little bit about, given what we know about the history of the observatory and its impact on astronomy, are there any themes that as we think about observatory programming going forward, any themes that you might say we should really try to build on this for the 21st century with students as they're coming through here?
Well, I'll take a stab at that for openers. I think the issue is the importance of regular, precise observations in astronomy over long time periods, which give you, they can be done visual with a telescope, or they can be done photographically, or they can be recorded automatically. But just the importance of observations in pushing a field forward.
Yeah, I was thinking along very similar lines that, having an observatory where people, and, you want to say the students will have hands-on training and really take observations and run with them. It's just so essential to developing great scientists. The one kind of caveat that I had in hesitating saying that was, as one of the other of you already mentioned, Watson was famous for preventing students from actually using the telescope. But nonetheless, clearly he did train some very important people, like Schaeberle, for example. So I think it does go to show that great facilities lead to great training and great scientists and the progress of science.
Mm-hmm. Okay. Andrew, anything you'd like to add?
I think key theme, I agree absolutely. But I think another theme that's sort of a valuable thing to keep in mind is sort of contributions of science to society, both historically into the present day, with astronomy being used for time or navigation, finding longitude or latitude. So I think it's really valuable with something like the observatory, which is an incredible resource, about not only how it prevents science or how it helps science operate and advances it, but also how that science is then turned to the benefit of society. And I think that would be a really interesting thing for students and anybody who's interested.
Okay, well, great. Thank you all. I think this has been a great panel and a great discussion. I want to say to the audience, we have another one in just a little bit where Robert Stenzel recently retired from the Cincinnati Observatory. Dean Regas, who is the astronomer at the Chamberlain Observatory for Stenzel, Cincinnati Observatory for Dean Regas, and Michelle Mclaughlin, a historian from the Bentley, are going to talk about the uses of facilities like an historic observatory for contemporary education. And I hope you'll be able to join us. So Andrew, Sally, and Pat, thank you again. And we'll see you sometime soon, I hope.